Thank you very much, Valdas. Good afternoon, everyone. As Valdas has said, we will talk a bit about artificial intelligence here in SAFE4SOC. In this case, the main idea is that this AI is not the more common and nowadays hot topic of AI based basically in interaction between users and systems. In this case, these AI systems that we have developed and integrated here are those systems that are able to analyze patterns, extract patterns, identify this type of patterns that make easier the work for the operators in this case, not specifically designed to interact with them, but to provide better information and also to create complex patterns. Why we will do that? Because as we know, in this last, 4 years, the incident management has been managed by a lot of tools in different domains, as has been explained by Gilles before, in the cyber realm, in the availability, or in the physical part. The SOC processes that integrate this and that arise decisions or actions to do this information are not standardized right now. In fact, the experts of each topic or domain are different. The standards usually are different. This is quite complex. And also, if we have a multi-SOC system, there are a lot of information that is generated by each one of different nature and in some cases related between them. So in this case, as we part from a very wild origin where you need a lot of tools, a lot of experts in those tools, there are different threats that cannot be identified by using only one tool or only one expert. We think that we need better tools to use information in a complex carpet and to emerge the threads of high level that we can use to do that. In that sense, we create AI to analyze these complex patterns. I think that is the best way we can use that. And in that sense, we try to cover all of the different or the main channels where these incidents might arise in the tradition and in the IT systems. For example, we can work with the network traffic. We can also work with industrial events. We can work also with log files, and at the end, we can also integrate them in heterogeneous graphs of all of these events. For this idea, we have developed four tools that are mainly focused in one of these sources, but it can analyze this source in a low-level analysis to avoid dependencies with other systems, and later they can be reported and provide high-level information. So the first one is Sigmoids. Sigmoids is a real-time anomaly network-based intrusion detection system. The idea here is to be able to use AI to extract patterns by taking into account the real time of IT networks, mainly to be able to work with all of the data that we have, but also to adapt to other industrial or critical entities traffic that can be in this sense also real time. And the idea here, what is the main features? The main feature is trying to identify new and large specter cyber attacks very quickly. In a second, it will be updated. But taking into account that this should be done using unsupervised analysis, so we don't have signatures, we don't need previous patterns. The patterns are extracted and analyzed, and at the end, One, we have realized that we obtain very low false positive rates. We create IDMEF alerts that can be inserted in the system, in the Concerto, to be able to increase this information, or to enrich the information of an event with this network data analysis. The second tool is Hendrix. Hendrix is related with the industrial control systems events. In that sense, we know that there are a lot of tools that work with host and network, but with embedded devices, the famous AOT is complicated because they use less known operating systems. They use other file systems. So in that sense, these kernel are usually outside of the radar, are not used or detected. So in this case, this tool, the focus of these tools is to work in this level. And the results we have obtained here is a detector using AI that identify patterns, anomaly scores every 2 seconds about the events of these embedded devices. And when we realize too that we obtain very low false positives, we raise an IMF2 message to be able to connect with the rest of the system. The third tool in this case is heterogeneous graph neural network, HGNN. In this part, this is a high-level tool that are able to integrate and to extract complex patterns using different types of entities. These entities could be IP, it could be a device, it could be a log file, it could be a person, it could be anything we can think of. In the sense here is to create graphs, networks of connections, and to analyze the patterns created in these networks, trying to identify anomalous patterns there to be able to highlight the biggest, the higher abstract events. In that sense, as I have said, it can handle multimodal signals, try to capture the complex contextual relationships between those entities, and also creates an alert to be able to transfer and to add to the context of the event. The last one is called ALMA. ALMA is the tool used to create high-level alerts in low-level events, low-level logs, sorry. In this case, the idea is that as we have all of the information to traceability for almost all of the operating systems and applications in logs, the idea here is to create an AI system that automatically can grasp a log to extract information, to create patterns, and to analyze automatically the anomalies that are described in those logs. The idea here is to be able to generate automatically a detector for a new type of log, mainly because there are a lot of private or undocumented anomaly applications whose logs are not as well covered as this log, and in that sense are nowadays out of the radar, and in that sense we are trying to use them to include in the analysis process. In this case, we work at two levels. One of them is to create anomalies in the sense of the template that is received in the log, and also to use anomaly identifying the values that these templates carry on as information to the system. This information can be extracted mainly directly from log files, but can be also intercepted as syslog messages from the network, or even if we have a Kafka queue where this information is processed by some tools, this can be analyzed, and in that sense create a detector to detect anomalies on that. In this case, right now, in this moment in the project, these tools has been updated and tested in the SAFE4SOC code repository that you have seen in the previous presentations. These tools has been also provide to define the AI-based multi-source analysis and the use cases that we will show in a moment, and also interesting to define a fine-grained definition of the pilots about which type of information we can deal with to create the best alerts and integration of tools, the tools of this SOC and the new ones that we can provide. And we are working to integrate them in the SAFE4SOC demonstrator that it will be shown afterwards, after this presentation. So the idea here is to create and integrate these tools in the automated data flow. As I have said, is not directly to interact with operators, but to interact with the data and to provide enriched information to the system. And now I will give the floor to my colleague Mindaugas, that will explain the process, the pipeline, about how this multi-source threat analysis can be used in Relay.
Thank you, Raúl. So yeah, now I will introduce the multi-source threat analysis scenarios, starting from the architecture and AI module placement. At the bottom, we have several local SOCs. Each SOC collects some local alerts and sends them through the information sharing gateway. The central SOC receives these alerts and passes them to the AI analysis component. The component analyzes these alerts and produces higher level meta EDMFAQ messages. On the right side, we show the outputs of the AI analysis dashboard. It has visual analysis, recommended actions, and can generate meta EDMFAQ alerts. We also have optional LLM explainability layer. It is not the main detection mechanism. Detection is still based on the structure correlation and similarity scoring. The LLM layer helps the detection by explaining the results, answering analyst questions, and making recommendations easier to understand them. So here are the three scenarios that represent multi-source threat analysis. Scenario one is about the sequence and early warning. One entity already shows a major attack chain, while others show only the early stages. Scenario two is about the parallel campaign clustering. Several SOCs may each see one of the local incidents, but centrally these incidents may look like one of the coordinated campaigns. And finally, the scenario three is different because it's based on the hazard anomaly detection, where the weather, context, and sensor data and availability alerts rise together above the normal baseline. So the key distinction is that scenario one is about the sequence, scenario two is about the similarity, and scenario three is about the external hazard context. And I will show a brief demo on the scenario two. For scenario one, it focuses on attack chain reconstruction as early warning. For example, one entity alpha has already shown the complete attack chain, for example, brute force, compromise, lateral movement. Other entities such as beta or gamma may show the only first stages. Locally, these alerts may look like ordinary failed logins or low priority activities, but when you combine it in the central AI component, these sequences show that some of them can be linked to the major one that is already fully, shown the full attack chain. So the output is early warning meta alert in the EDMFAQ format. So the main benefit is preventive action. The analysis gets stage-by-stage evidence and can predict the next step. So the scenario two focuses on coordinated campaign detection across multiple SOCs. Here, this activity is not mainly sequential, but it's in the parallel. Several SOCs each see a local medium priority incident. For example, SOC A sees SSH brute force, SOC B sees the login attempts, and SOC sees some VPN exploits attempts. Individually, all these SOCs might treat it as a separate local incident, but centrally, the alerts share the evidence and similar time, similar IP ranges, and similar targeted services. So the central AI can group these alerts to the one like discover the campaign. The output of the also of this scenario is the message that can be shared through the SOCs. For the scenario 3, it demonstrates a different type of detection. Here, the primary cause is not the malicious. The scenario is driven by the natural hazard. For example, a heat wave. Hazard feed reports the heat wave, and at the same time, sensor shows the temperature or cooling problems. Also, monitoring systems start reporting availability alerts. So the AI can compare these stations with the normal baseline. If the activity is above the baseline and aligned with the hazard context, it raises a section. It can raise an anomaly report based on this hazard. So the important part is that these are not marked as malicious, but it is marked as hazard causes. The main benefit is early cascade warning, preventive action, and cleaner situation awareness. So I will show you a brief demo on scenario 2. So this was a brief demo on the scenario 2. So for conclusion of our section, the system provides a central situation awareness across multiple SOCs, entities, and data sources. This is important because some patterns may be invisible to one local SOC alone. AI-assisted correlation, clustering, and anomaly detection helps operator handle large numbers of events. Also, the analyst can combine network and log sources of industrial low-level events. Also, the optional LM RAG layer can support summaries, Q&A, and adaptive recommendations. Also, the outputs are reusable because it generates IDMF v2 messages that can be shared through the architecture. So the overall goal is to give a local SOCs a shared central view, earlier detection, and better context while keeping information sharing controlled. So that's it for our presentation.